The undisputed observational evidence is that the moon moves across the sky from east to west, and the solar eclipse shadow moves across the Earth from west to east, which begs the question.
Dear Science, about that eclipse that's happening in August, I heard that the shadow is moving from west to east. But how can that be possible, since the moon moves from east to west?
To try to make it as simple as possible, it really boils down to how fast the Earth is spinning and how fast the moon is orbiting around it. The moon is orbiting about twice as fast as the Earth is spinning.
And the moon is overtaking the rotation of the Earth. And that is why the shadow of the eclipse is traveling from the west coast to the east coast.
The shadow is moving in this direction at 2,000 miles per hour, while the Earth's surface is moving at 1,000 miles per hour. So this overtakes it, and that's why it goes west to east.
Okay, the official explanation from scientism is that the moon orbits about twice as fast as the Earth spins, and therefore overtakes the rotation of the Earth, causing the shadow to move from west to east across the Earth. Let's test that theory. This is a 1 mile long racetrack. It takes the red car 1 hour to do a complete lap because he goes 1 mile per hour. The blue track is 2 miles long, twice the distance of the black track. How fast must the green car go to keep pace with the red car and finish his lap at the same time? 2 miles per hour, right? The green car needs to go twice as fast to keep up with the red car because he's traveling twice the distance. But what if the blue track was 5 times longer than the black track? The green car would have to go 5 times as fast, right? And if the blue track was 10 miles, the green car would have to go 10 times as fast, right?
Just like spokes on a bicycle wheel. The further away you get from the hub, faster the velocity is of an object that's attached to the hub, which means one is moving a lot faster. While remaining at the same angle from the center of the hub, the distance is much greater. So therefore, the speed that it needs to be traveling to make one revolution is greater at the further distance.
Okay, using Sly's diagram and NASA's official figures, the surface of the Earth at the equator rotates 24,901 miles on its axis at 1,040 miles per hour. And let's say this closer dot is a geostationary satellite, which we're told has an orbital circumference of 165,000 miles and travels at 6,864 miles per hour. The distance it must travel is 6.6 times as far as the surface of the Earth rotates. And so to remain stationary with respect to the Earth, it must go 6.6 times as fast. The outermost dot is the moon. We are told its orbital circumference is 1,423,000 miles. That distance is 57 times greater than the distance the surface of the Earth rotates. So in order for the moon to keep pace with the rotation of the Earth, it would have to move 57 times faster. It would have to be going 59,280 miles per hour. And remember, that's just to keep even pace with the Earth. In order for the moon to overtake the rotation of the Earth, it would have to be moving even faster than that. But according to the experts, the moon only travels at 2,288 miles per hour. Do you understand what this means? In order for the solar eclipse shadow to move across the Earth from west to east, they need the moon to overtake the rotation of the Earth. It's the only way it could happen in their model. But in order for the moon to overtake the rotation of the Earth, it needs to be traveling at greater than 60,000 miles per hour, or about 58,000 miles per hour faster than they tell us it goes. And those are only the mathematical problems. What about the observational ones? If the moon did go 60,000 miles per hour and overtake the rotation of the Earth, people on the Earth would see the moon going west to east across the sky. Let me show you using Sly Sparkane's animation. The black line is the moon's umbra. Watch the moon overtake the rotation of the Earth and cause the shadow to go from west to east across the United States. Let's have a closer look. The first problem is that a person standing here on Earth would be watching the moon set in the east as the sun comes up. From his perspective, the moon is setting into the rising sun. When has anybody ever witnessed the moon set in the east? Now imagine you're standing here in Oregon at the start of the eclipse. Which direction is the moon moving across the sky from your perspective? As you can see, the person in Oregon would have watched the moon go west to east across the sky. Of course, that absolutely must be the case if the moon overtakes the rotation of the Earth, right? In their scenario, the moon must go across the sky from west to east. It's the only way to get the shadow to move from west to east across the Earth. And what if you were standing here on the Earth? You would see the moon rise in the west just as the sun sets. Of course, nobody's ever seen the moon rise in the west, right? So yeah, Sly Sparkane, your animation is just as messed up as NASA's model. This is big, people. A lot of us moved on from the solar eclipse shadow problem when Jaron did a video saying that the math works out. He was misled and he was wrong. Please help me get the word out about this unequivocal refutation of the heliocentric model. Share, mirror, trim, edit, do whatever you want with this video, but let's spread the word far and wide about how their model simply can't work.